as our final example, we'll do example number 9. Now, number 9 is an example that's quite different from any limits that we've done in the past. If you notice that in this limit problem, there's two different variable types. We got x and h. Now notice, as far as the limit is concerned, since we're taking the limit as h approaches 0, if you were to make a table of values, let's say using numerical method, then you would pick values like zero point 0.1, zero point 0.01, 0.001. But you would be picking these values for h, not for x. So what we're going to do, we're going to do this limit, we're going to treat x as though it's a fixed value, a constant, and the variable in question here is h, since the limit is being taken with respect to h. So the first thing I'm going to do, since it's a quotient, I begin by, again, looking at the limit of the denominator. Well, the denominator is just the identity function. So the limit of the identity as h is approaching 0 is just 0. So then again, I check the limit of the numerator. Now, if you look at the numerator is a difference of two functions. One of the functions, and I'll circle this one in green, the x to the fourth is really a constant function, since we're assuming that x has a fixed value. The variable in question here is h. So we know that the limit, first of all, since the numerator is a difference of two functions, we know that the limit of the difference is a difference of the limits, and the limit of a constant is just a constant value. So the limit of x to the fourth as h approaches 0 is nothing more than x raised to the fourth power. And then the limit of x plus h raised to the fourth power, that's a power function. We do that by direct substitution, and that turns out to be x to the fourth as well, which gives us 0 for the limit of the numerator. So again, we're dealing with an indeterminate limit. So we're off to try to find this replacement function. Well, what catches my attention right away is that I have this binomial raised to the fourth power. So that tells me, kind of alarms me, to use the Pascal's triangle to expand the x plus 4, the x plus h raised to the fourth power. Since the original exponent is 4, I will need the fifth row of Pascal's triangle. So I'll do it over here on the right. So there's our coefficients that we'll be using. So the numerator becomes x to the fourth plus 4 x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. And don't forget, there is an x to the fourth already in the numerator. The denominator is h. Now, looking in the numerator, I notice that the x to the fourths cancel out. And I'm left with 1, 2, 3, 4 terms in the numerator, and all of them contain a factor of h. So I'll factor out the h. And now notice there's another cancellation that takes place, but a division type. Well, this function that we have right here in the parentheses, that's our replacement function. So the question is, saving, just give me a minute here. Okay, here we go. The question is, what kind of function is a replacement function? Well, notice that the variable in question is h, and since we have all natural number powers of h, this is nothing more than a polynomial function in h. So how do we find the limit of a polynomial function? That's right, direct substitution. So I will be replacing h with 0. As I do that, notice that the second term is going to go to 0. Third term goes to 0. The fourth term goes to 0. So what we're left with is 4x cubed. That is the limiting value. Now, this example, like I said, is different from the others in the following sense. Look at the final answer. The final answer is not a number, but it's an expression in x. If we assume that x is a real number, then this will be a real number expression.